Good evening, everyone. Today, myself, Adithya Vipin, and my teammate Amrith Thejas will be presenting our AAT based on the topic Dragonfly Optimization Algorithm, which is one of the important nature inspired algorithms from our syllabus. This algorithm belongs to the class of swarm intelligence techniques, and it is inspired by the extraordinary hunting and the swarming behavior of dragonflies in their particular nature. So, the presentation will walk you through the biological inspiration, the mathematical modeling, the internal mechanics, the workflow, the applications, and finally the pseudocode that defines how the algorithm works computationally. So, in today's session, we will start by understanding what nature inspired algorithms are and why the dragonfly's behavior is so interesting for optimization. We will then move on to the objectives of the Dragonfly algorithm, what exactly the algorithm aims to achieve, and why researchers prefer it over some of the traditional methods. Next, we will dive into the core part, which is the mechanics and the behavioral rules that govern the swarms. Once that is clear, we will walk through the workflow and implementation, including a very helpful flowchart to visualize the steps. We will then look at the applications to understand where the algorithm is actually used in real life. And finally, we will wrap it up with the pseudocode, which gives us a complete technical summary of how this particular algorithm works. So, nature inspired algorithms are becoming extremely powerful in optimization because they mimic natural processes that have evolved over millions of years. Dragonflies, for example, show highly coordinated behaviors during hunting and migration, and they exhibit patterns like maintaining formation, avoiding collisions, moving towards a particular prey, as well as escaping predators, all of which resemble problem solving strategies. The Dragonfly optimization algorithm captures such behaviors and uses them to solve computational problems. Each dragonfly in the algorithm represents a possible solution, and the movement of each dragonfly represents how the solution evolves over time. DFA is especially useful for high dimensional problems, non-linear optimization problems, multi-objective optimization, as well as avoiding local minima. And because of such strengths, it is commonly used in machine learning tasks like feature selection, clustering, and even tuning neural networks. Now, moving on to some of the objectives of Dragonfly algorithm. The algorithm has several important objectives. Firstly, it aims to balance exploration and exploitation, which are two essential components of any optimization method. Exploration helps the algorithm search widely across the solution space, while exploitation helps it refine the best solutions more deeply. A second, DFA aims to achieve stable and smooth convergence. Some algorithms converge too fast and get stuck in local minima, while others converge too slowly. DFA tries to strike the right balance. Another objective is to make the algorithm robust for nonlinear and complex functions, especially those where classical gradient based methods fail. The algorithm also avoids premature convergence by incorporating enemy distraction behavior, which pushes it away from low quality solutions. And finally, the Dragonfly algorithm tries to keep the computational cost low. Unlike some other algorithms with many tuning parameters, DFA is relatively lightweight and also easy to implement. Now, talking about some of the dragonfly patterns or the classification of the dragonfly patterns. In nature, dragonflies normally exhibit two major patterns of movement, the static swarming and dynamic swarming. In static swarming, what happens is when dragonflies gather around prey, they stay relatively close to a fixed position, and this behavior resembles exploitation because the swarm is focusing on a specific promising area. Dynamic swarming, on the other hand, occurs during migration. So, dragonflies move across large distances while maintaining formation, and this resembles exploration, where the swarm searches new regions for better solutions. These two behaviors, static and dynamic, are the foundation of Dragonfly algorithm, helping it to alternate between focusing and exploring. Now, moving on to some of the mechanics and the behavioral modeling of the Dragonfly algorithm. Let's break down the five key behaviors that govern the movement of dragonflies. Initial stage is separation, so this prevents dragonflies from crashing into each other. In optimization, it helps to avoid overlapping or redundant solutions. Secondly, alignment. Here, each dragonfly attempts to match the direction and the speed of its neighbors. This promotes smooth convergence and cooperative movement towards better solutions. Thirdly, cohesion. This behavior pulls each dragonfly towards the center of its neighboring group. It helps to maintain swarm stability and encourages solutions to move as a collective unit. Fourthly, attraction towards food. This is where dragonflies move towards the best solution that has been discovered so far. It represents exploitation, helping refine the optimal area. And fifthly, distraction from enemy. So this pushes the dragonflies away from the worst solution found. It helps maintain diversity and prevents the algorithm from getting stuck in low quality or local minimas. All five of these behaviors together allow the swarm to update positions in a coordinated and intelligent manner. Now, moving on to the mathematical modeling aspect of the algorithm. Mathematically, the algorithm combines five behavioral forces into a single step vector. The step vector delta x is computed by taking weighted contributions from separation, alignment, cohesion, foot attraction, and enemy distraction. The updated position of each dragonfly is then calculated by adding the step vector to the current position. Although the formulas look really simple, they model very complex swarm dynamics. These equations ensure that the swarm naturally moves towards the optimal region while still maintaining enough randomness and diversity to explore the search space. Now we'll be talking about the general workflow and implementation of the Dragonfly algorithm. Let's walk through the workflow step by step. So the process starts with initializing the dragonflies, placing them randomly in the search space, and next we evaluate the fitness of how each dragonfly performs to determine how good each solution is. And based on that, the algorithm identifies the food source, which is the best solution, and the enemy, which is the worst. The behavioral forces such as separation, alignment, cohesion, foot attraction, and enemy distraction are then computed for each and every dragonfly. Using these forces, the dragonflies update their step vector and move to the new positions. If the swarm becomes too stagnant or doesn't find any neighbors, the algorithm uses Levi flight, which helps dragonflies explore distant regions and escape traps. The entire process continues until the stopping condition is met, either a maximum number of iterations or a particular desired accuracy level. And the final output is the best solution discovered during the search. So now let's look at the representation in a flowchart aspect. So this flowchart summarizes the entire workflow visually. We start with the initialization and the fitness evaluation. If dragonflies have neighbors, the algorithm applies the five swarm behaviors, and if not, the algorithm switches to the Levi flight to encourage global exploration, and then the positions are updated, fitness is recalculated, and this loop continues until the algorithm converges. Finally, the algorithm outputs the best solution, and this flowchart is extremely helpful in visualizing the control flow of this particular algorithm.
Uh, Hello ma'am, my name is Amrith and I'll be talking about rest of this presentation starting from the pseudocode slide. The pseudocode is a simplified software like representation of full process. Anyone familiar with the program or the optimization techniques can directly implement the algorithm by following the structure. Uh, Anyone can use this structure and implement the algorithm very easily ma'am. Okay, moving on to the application. Uh, okay, applications of Dragonfly optimization. We can start with machine learning. Dragonfly optimization is widely used in machine learning tasks such as feature selection, hyperparameter tuning, and clustering. It helps the model to choose the most relevant features and can improve the accuracy. Also, it is used in neural network optimization, helping the model converge faster while avoiding local minimas. It provides the model to be more efficient and more less time consuming. Engineering design. In engineering, DFA is applied in areas like structure optimization and control system design. It helps find the best design parameters while reducing cost or the weight. It is also used in optimizing energy, such as for better efficiency. Image processing. In image processing, the algorithm is effective in tasks such as segmentation, threshold, etc., and most importantly, pattern recognition by optimizing pixel-based decision boundaries. It enhances the image clarity and helps better in object detection. Wireless and sensor network. It is used in detect the best routing path, cluster nodes efficiently, and allocate resources in communication system. This improves the network. This improves the network performances and reduces delays. Scheduling and operation research. The algorithm helps in optimizing the scheduling, resources, and decision making industries. For example, assigning tasks efficiently to reduce time and cost in manufacturing or logistics. Okay, moving on to the key findings and observation. First one is strong optimization capability. The algorithm is very efficient in solving difficult optimization problems because it combines both global and local search strategies using biological behavior. Ability to avoid local minima. The swarms jumps out of the low quality areas and explores better solution instead of getting stuck. Simple yet flexible design. The algorithm is very easy to implement since it requires very few parameters. Despite its complexity, it performs competitively compared to other complex optimization techniques. Wide applicability. It is successfully used in AI, engineering optimization, and because of its adaptability to different problem types. Okay, since we talked about the key findings and observation, we'll be moving on to the advantages of Dragonfly. Okay, advantages of Dragonfly. We can start from balance search ability. It manages both exploration and exploitation well. It reduces the premature convergence and improves the final solution accuracy. Moving on, simple and easy to implement. It has few parameters, making it lightweight, computationally efficient, and easy for researchers to apply. Then, moving on to avoids local minima. The enemy avoidance mechanism helps the swarm escape from low quality solution and reach a better global solution. High versatile. It works well for both continuous and discrete problems and is applicable in AI engineering and data science optimization. Okay, moving on to the limitations. Limitation faced by Dragonfly algorithm is parameter sensitivity. The performance greatly depends on the proper selection of parameters such as weight, radius, and population size. Pure tuning leads to weak optimization. Okay, slow convergence in complex spaces. In very high dimensional or rugged search spaces, convergence can be slow if the behavior of the forces are not balanced correctly. Okay, swarm stagnation. If diversity drops with the swarm, algorithm might fail to explore new areas and can stagnate around a single solution, which causes a problem for Dragonfly algorithm. Then comes the computational cost of large populations. When swarm size is large, the calculation required for each iterations can significantly increase, reducing in higher computational time. Okay, this ends with the limitations. Conclusion. To conclude, we can say that the Dragonfly optimization algorithm successfully translate neural swarm behavior into computational techniques. By modeling 5 behavioral components, it maintains an excellent balance between exploration and exploitation. Okay, the algorithm excels at escaping local minima due to enemy avoidance and levy flight. improving its global search ability. Its simple structure and low parameter requirement makes it easy to implement while remaining powerful compared to other algorithms. Because of its flexibility, DFA has been used in effectively in machine learning and engineering design, let's say image processing, etc. Overall, it offers a reliable and efficient solution for solving complex optimization problems inspired by nature. Okay. References, we have taken the references from Mirjali's Dragonfly algorithms, Mirjali's whale optimization algorithms, Yang S nature-inspired meta-heuristic algorithms, ResearchGate flowchart of Dragonfly algorithms, MDPI journals, application of Dragonfly algorithm in optimization and machine learning. Uh, by saying this, I conclude my presentation in Dragonfly algorithm. Thank you, ma'am.